Welcome back. Up to this point in the course, we've spent time reviewing several important topics from your first two methods classes. In particular, we have been looking at inference procedures for population means, hypothesis tests for a single population mean, as well as how to construct confidence intervals for a single population mean. We then looked at how to compare two population means via hypothesis testing, as well as how to construct a confidence interval for the difference between two population means. And we did this in the context of t-tests. And then we generalized that and looked at how to compare the means of two or more populations using analysis of variance. And we followed that up with how to perform custom hypotheses, whether it would be doing pairwise comparisons or some other types of contrasts of interest, using linear combinations of the response variables to test those hypotheses. In each case, we have looked at how to do the calculations, whether we're talking about the one-sample z-test, the one-sample t-test, the two-sample t-test, and then finally analysis of variance. So we looked at how to perform those calculations. And one important point to be made is that the method of analysis, whether it would be analysis of variance or some form of a t-test, for example, the method of analysis depends on the way that the data have been generated, the way that the data have been gathered. So, for example, if you're in a sampling context, sampling from one or more populations, the methods or the method by which one samples the populations will determine the proper method of analysis. In an experimental situation, the way that one conducts the experiment will also determine the way that the data should be analyzed. And so it's very important that we understand the different ways of performing designed experiments, the different kinds of experimental designs that are out there, the reasons for using the various experimental designs. And once a design has been selected and used in an experimental situation, being able to identify the design that was in fact used so that the proper method of analysis can be determined and carried out. Now, in much of the experiments that get conducted, there are more than two population means to be compared, and so analysis of variance is the approach that is generally used to analyze the data from those kinds of experiments. But again, the way that the experiment is conducted will have an impact and in fact will determine the proper way of doing that analysis of variance. So in your first methods class, you learned how to do analysis of variance, and like I said, we reviewed that. In your second methods class, you may have expanded your repertoire of experimental designs, but perhaps that didn't happen, and that we're going to be looking at a number of experimental designs in this course. But if you did have that experience of looking at perhaps one or two other designs, you can attest to the fact that the design of the experiments impacts the way that the data are analyzed. And so it's very important that we be able to identify different experimental designs and that we use the appropriate method of analysis that correspond to those designs. So taking as an example the analysis of variance procedure that you've learned in your first methods course, your instructor may or may not have identified the particular experimental design that was being assumed for those calculations. That is going to be the topic of this lecture video and subsequent lecture videos for the next few days. And so that design that was assumed in teaching that first approach to analysis of variance, that design is called a completely randomized design. So let's take a look at this. We'll first talk about the components of an experimental design. Now, you'll remember from our introduction to the course, we talked about some of these concepts, and we did talk about the components of an experimental design. I'm going to use some slightly different terminology in this particular lecture that we will be utilizing throughout the rest of the semester. But it's important that we understand the components of an experimental design so that we know how these different designs, we know how, in what ways, in what aspects, these different designs can vary. And so let's talk about first the components of an experimental design. And so one way of thinking about the components of a design is through the treatment structure and the design structure of the experiment. Now, the treatment structure for an experiment is the set of treatment combinations that are to be used in the experiment. So you'll recall that when we first talked about these kinds of things, we talked about factors. And factors are those conditions or interventions that are under consideration in a particular study. And factors typically have 2 or more levels, and you may have more than one factor. And so the combinations of the various factors, the various levels of the factors that are used in an experiment comprise the treatment combinations to be used in the experiment. And so the treatment structure of an experiment corresponds to the set of treatment combinations that are going to be used in the experiment. The design structure is or relates to the manner in which the experimental units are grouped. Now, you'll recall that the experimental units in an experiment consist of the experimental material to which a particular application of a treatment is applied. All right, and so when we think about the design structure, we're thinking about how are we grouping the experimental units in the experiment. Now, in some designs, we really don't group experimental units, but in many of the designs that we'll consider, in fact, most of the designs that we'll consider, we do group the experimental units in one or more ways. And the reason for doing that, we will discuss more in depth in the future, but basically it's to ensure that the experimental units are grouped into groups or blocks where the experimental units are homogeneous or very much alike within those groups. So the components of an experimental design consist broadly of the treatment structure for the experiment, the design structure for the experiment, and then thirdly, the method by which treatments are randomly assigned to the experimental units. So the way that the treatments are assigned to experimental units is very, very important. We cannot neglect to consider that because that really is the defining feature of an experimental design. So experimental designs may have similar treatment structures, similar design structures, but they may use, or different experiments may use different methods of assigning the experimental or treatments to experimental units, and so therefore that would constitute a different design. So these are the 3 components that we'll typically be focusing on when we consider the different experimental units that we look at in this class. Now, there are some assumptions that are made regarding the treatment structure and the design structure of an experiment. The first is that the components of the design structure are assumed to be random effects. And so one example of that would be that blocks used in an experiment, for example, in a randomized complete block design, which we'll look at after we get done with this particular design. And again, you may have looked at that type of design in your second methods class. It would typically not be covered in the first methods class, but oftentimes is in the second methods class. And so in a randomized complete block or RCB design, the blocks used in the experiment are almost always considered to be a random sample from the population of possible blocks of experimental units. And so, in other words, the blocks are considered to be random effects. That's one of the reasons, well, it's the reason why when you are performing a random analysis of variance for a randomized complete block design that you use proc mixed, because proc mixed has the capability to incorporate blocks as a random effect. Okay, so that's the first assumption, that the components of the design structure are consider to be random effects. The second assumption is that there is no interaction between the components of the treatment structure and the design structure. Now, another way to say that, or to think about that, is that the relationships between treatments are the same from one block to another. In other words, that different blocks do not affect the relationships between the treatments differently. All right, so you have this uniformity of relationships between treatments from one block to another. Now, that may or may not be the case, but in most of the designs that we will look at, this assumption has to be made. Otherwise, you would need even additional replication to be able to test that. So those are a couple of the assumptions that exist. They're made regarding the treatment structure and the design structure of an experiment. All right, now let's talk about the method of assignment of treatments to experimental units for a completely randomized design. Now, let's denote the number of treatments by T and the number of experimental units to be used in the experiment by N. So N is the total number of experimental units that are to be used in the experiment. Now, in a completely randomized design, or a CRD, the T treatments are assigned to the N experimental units completely at random. Now, what does that mean? Well, specifically what this means, the way that it's carried out, is that treatment 1 is assigned to a number of experimental units randomly selected from the N units, and the number of experimental units to which treatment 1 is assigned will be denoted by R1. All right, and so R here represents replication, all right, or replicate, and so R1 is the number of experimental units that treatment 1 is applied to, and the way that the assignment is done is that we have N units, we randomly select R1 experimental units from the N units, and then we assign treatment 1 to those units. Treatment 2 is assigned to R2 units that are randomly selected from the remaining N minus R1 units, and so on, until we get down to the last treatment. And by the time we get to the last treatment, the remaining units, which is denoted by R sub T, so the number of experimental units to which treatment T is assigned, which is obviously N minus the sum of the previous numbers of replications or numbers assigned. The treatment T gets assigned to the remaining values. All right, so that is the mechanism. It's the method of assignment of treatments to experimental units for a completely randomized design. Now, what are the implications of this method of assignment? Well, with this completely random method of assignment of treatments to experimental units, every possible allocation of treatment 1 to R1 units and treatment 2 to R2 experimental units, and so on, down to treatment T being allocated to RT experimental units, they all have the same probability of occurring. All right? Every possible allocation for these assignment numbers, all right, replication numbers, have the same probability of occurring. Now, one implication of that, and in fact, let me just say that this is really the defining feature. This is the defining characteristic of a completely randomized design. All right, if we go back to this slide here, where we talk about the components of an experimental design, and one of the most important components is the method by which treatments are randomly assigned to the experimental units. All right, and so this characteristic is really the defining feature of what constitutes a completely randomized design. Now, one implication of this defining characteristic is that each experimental unit has the same probability of receiving each of the T treatments. All right. And some resources that you will look at actually list this last bullet point as the defining feature, the defining characteristic of a completely randomized design. But that's actually not quite correct, because it's possible for the second bullet point to be true, but the first, this defining characteristic up here, to not be true. And we see the same kind of thing in sampling designs. All right. If we satisfy this particular defining characteristic, that every possible allocation of these number of replicates, of each of the treatments to this number of replicates, having the same probability of occurring, that implies this last bullet point. But this last bullet point does not imply that defining characteristic to be satisfied. So it may seem like a minor point, and we're not going to get hung up on it, but I just want you to be aware of this, that this first bullet point really is the defining characteristic of a completely randomized design, and it has as a ramification or an implication this second bullet point, that each experimental unit, whichever one we're talking about, has the same probability of receiving each of the T treatments. All right, so let's look at an example. This will be example 2.1. So suppose that T equal to 5 treatments are to be assigned completely at random to n equal to 20 experimental units, and that each treatment is to have equal replication, so that the replication numbers, R1 through R5, are all equal to 20 over 5, or 4 reps for each treatment. Now let me just stop and say that in general, for a completely randomized design, you do not have to have equal replication, but there are some advantages to doing that. Number one is that, and this is probably the most important, is that for a given sample size, with equal replication, you're going to have the most power. The second advantage is that it simplifies the analysis, which is relevant if you're doing the analysis by hand, but if you're doing the analysis using statistical software like we will typically be doing, that's not as big of an issue. All right, but again, equal replication does give you the greatest power. Now, with this completely random method of assignment, the number of possible assignments is equal to this very large number, 3.05540235 times 10 to the 11th. All right, so there are a lot of possible assignments. And based on how we're, again, doing the assignment completely at random, all of these are equally likely. And so what that implies then, under completely random assignment, these assignments are equally likely, so that each has a probability equal to 1 over that very large number, and that turns out to be 3.27289138 times 10 to the minus 12. So a very small probability associated with each of those possible assignments. Now, in addition, and again, let's go back and look at what we talked about just a minute ago. One implication of this completely random method of assignment is that each experimental unit has the same probability of receiving each of the T treatments. And so, for example, if we consider experimental unit 1, then the probability that experimental unit 1 would receive treatment 1 is equal to 1 over 5, again, 5 being the number of treatments. The probability that experimental unit 1 would receive treatment 2 is again 1/5, and so on for each of the 5 treatments. And the same kind of statement would be true for each of the other experimental units in the experiment. Okay, so that's an example of what we've been talking about. So let's move on to the next topic, model for the completely randomized design. And this is perhaps something that you were not exposed to in your first methods class, perhaps not even in your second methods class. I guess it depends on who's teaching and their approach. Oftentimes, the approach to teaching analysis of variance, at least in a first methods class, and in the textbooks that are used in a first methods class, are to focus on how to do the calculations, right? Partitioning the sums of squares and determining the appropriate degrees of freedom, and once you have those, then you can compute the mean squares and finally the F statistic. All right, so the focus is on doing the calculations rather than understanding what the underlying model is. Well, in this class, we're going to be all about the model. Right? We will be doing some calculations, obviously, but we're going to be much more focused on these statistical models associated with these different designs than we were in the first methods class. For example, you may think about the t-test or the two-sample t-test. You may not have ever seen a model for those particular kinds of models, but they do have models associated with them. So the statistical model for the completely randomized design can be written in a couple ways. This is the first way we'll look at. All right, and so we have y sub ij equal to mu sub I plus epsilon sub ij, where again I goes from 1 to t. I is the index I corresponds to the treatment, and then the subscript j corresponds to the experimental unit receiving a particular treatment. Now in this model, y sub ij on the left-hand side here, this is the measured response on the jth experimental unit that has received treatment I. Mu sub I is the population mean response under treatment I. And then finally, epsilon sub ij is the random error associated with the jth experimental unit receiving treatment I. Now this epsilon sub ij, clearly from the model, this is the difference between the response measured on the jth experimental unit receiving treatment I and the mean response under treatment I. Now, the reason we need this random component, this random error term in the model is because different experimental units are going to respond differently, even if they are receiving the same treatment. So it would be, it's not at all uncommon. In fact, it would perhaps be unusual for different experimental units to respond in exactly the same way. All right? The reason they don't is because even though experimenters strive to have homogeneous experimental units, they're not completely homogeneous, and the differences that they do have impact the way that the experimental units respond to the treatment. And so because of that, there's variability in the responses of the experimental units that are receiving treatment I. There's variability around the mean, whatever it happens to be, for that treatment. And that variability is accounted for in the model by the error term. In other words, the deviation of the response from the treatment mean is allowed for, accounted for by the error term here. Okay, and so that's what each of those components mean. Now we can also express the statistical model for a completely randomized design using what's called an effects model. And by the way, again, this is called the means model. All right, the effects model breaks the mean under treatment I into two pieces, the sum of two pieces. All right, so if we go back to the previous slide, we have y sub ij being equal to mu sub I plus epsilon sub ij. And in the effects model, we are decomposing the mean mu sub I into the sum of mu and alpha sub I. Well, let's see what these components mean. Again, y sub ij is the measured response on the jth experimental unit that is receiving treatment I. Mu is the overall mean response across all treatments. All right, and then alpha sub I would be the effect of treatment I. And so mu sub I is just mu plus alpha sub I. The mu sub I, which is the mean under treatment I, is equal to the sum of the overall population mean across all treatments plus the effective treatment I, and that effective treatment I could be positive. Some will be positive, some will be negative, and in fact, the alpha sub i's will sum to 0. Okay, and then the epsilon sub ij has the same meaning as it did in the means model. All right, now let's talk a little bit more about the random error terms, the epsilon sub ij's. The error terms are random variables, and in particular, they are unobservable. All right, so if we go back here to either the effects model or the means model, if we consider what we, as experimenters, get to actually observe, we only get to observe what is on the left-hand side of this model, the response. Now, we do also know the treatments that are being applied, so that is really encapsulated here on the right-hand side. All right, so we get to observe the y sub ij's, but we don't get to observe, we don't know the true value of mu, we don't know the true value of I sub j, I'm sorry, alpha sub I, and we don't get to observe the random error terms epsilon sub ij. So we have to estimate all these quantities, and we do that by observing the response, observing the design matrix or the design variables, knowing which treatment an observation comes from. All right. So those error terms, the epsilon sub ij's, are unobservable random variables. By the way that the model is set up, the error terms have a mean of 0, and then they vary from one experimental unit to another, and so that variability is represented by sigma squared. All right, the variance of the epsilon ij's is sigma squared, and again, we don't know sigma squared. We have to estimate it from the data, and in fact, and as you know from doing an analysis of variance in your first methods classes, we have to have an estimate of sigma squared in order to perform hypotheses where we are comparing the means of populations. Okay, so the error terms are random variables. They have a mean of 0, and the variance of the error terms for this model, for this completely randomized design model, are that variance is sigma squared, and that's for all treatments and experimental units in the experiment. Now, in addition, for purposes of inference, we need more information. We need to make additional assumptions, let's put it that way, about the actual distribution of the error terms. And so that assumption is that the error terms, not only do they have 0 mean and variance sigma squared, but we also assume that they are normally distributed. Okay? And also, the error terms are assumed to be IID, so independent and identically distributed. Now, that is a function, whether or not they're independent is a function of how the experiment's conducted. And in order for this assumption to be valid, in order for it to be true, the experiment must be done in such a way that the responses from different experimental units are unrelated. They are independent of one another. And then finally, this last note down here, as I was saying up at the top of the slide, these assumptions that we have here imply that the random variation associated with the experimental units is the same under all treatments. Now, is that always true? Perhaps not. In fact, no, it's not. And that's why tests exist, hypothesis tests exist, to test that hypothesis, to test to see whether that's a reasonable assumption. You know, it's very possible that under different treatments, the variability that the experimental units exhibit could change. And so, that is something that needs to be tested. All right, and for example, SAS-Proc GLM and SAS-Proc Mixed have ways of testing that. But the standard assumption in analysis of variance for the completely randomized design, and for other designs as well, is that the experimental units have the same level of variability across all treatments. Now, what are the advantages of the completely randomized design? Well, the CRD is flexible in that any number of treatments can be used. In addition, any number of replications can be used. And on top of that, the number of replications does not have to be the same from one treatment to another. The number of replications can vary from one treatment to another. So you don't have to have equal replication, which is really nice and makes it more flexible. In addition, the statistical analysis of data from a completely randomized design is relatively straightforward and simple. As you saw in your first methods class, you were able to do that by hand, and so that would indicate that it's not too terribly computationally intensive and it's fairly straightforward to do. Different designs are going to have more complicated analysis procedures, and in many cases we won't want to do those by hand, all right? But for the completely randomized design, it's really not too bad. Another indication that it's relatively simple is that this was the first application of ANOVA that you were exposed to. So they didn't throw the hardest one at you. They threw pretty much the simplest design at you from the standpoint of analysis. Now, the other thing is that the CRD provides maximum degrees of freedom for error. So when compared to other designs that we'll look at, you'll see that the number of degrees of freedom that we have for error are going to be reduced in those other designs because we are partitioning the variability in different ways. And so the effect that has is that it decreases the number of degrees of freedom associated with the error term. And the impact that has, well, let me just put it this way. Having more degrees of freedom for error lowers the corresponding critical point from the F table, and so that's going to make it easier to reject the null hypothesis, and so it gives the test more power. So completely randomized designs, from the standpoint of degrees of freedom, have at least the opportunity to be more powerful. Now, having said that, notice that I did not say that completely randomized designs are always more powerful. That's certainly not the case, and that's not going to be the case, for example, when precision is low because the experimental units are not homogeneous. So we're now that leads us into some of the disadvantages of completely randomized designs. That being that if the if the experimental units are not very homogeneous, if there's a lot of variability, if there's a lot of heterogeneity among your experimental units, then the precision that is afforded by the completely randomized design is going to be low. Now, what that means is that the variance, let me go back here a few slides, okay? The variance, if your experimental units are very homogeneous, and if you're using good technique and measurement and things like that, then the variance of the error terms will be fairly small, and you'll have more power. But if your experimental units are not homogeneous, if they've got quite a bit of heterogeneity, all right, then what that's going to do is that the variance of the error terms is larger, and when that's the case, then you lose precision. And so, even though there might be an advantage to the completely randomized design by virtue of it providing maximum degrees of freedom, which for error, which again reduces the critical point needed to reject at a given significance level. If the precision is low, that increase in the degrees of freedom that we have here is offset, and sometimes more than offset, by the decrease in precision. So this is one of the disadvantages of the completely randomized design. If your experimental units are not homogeneous, then the precision of the experiment can be low. Now, this becomes a problem. This lack of homogeneity becomes more and more of a problem as the experiment gets bigger and bigger, in particular as the number of treatments increases. And this can be a problem in, for example, factorial experiments where you've got a number of factors, each at multiple levels. As the number of factors increases, if you are performing a factorial experiment, then the number of treatment combinations increases very quickly, and it can be very difficult to find enough experimental material that is homogeneous in order for a completely randomized design to be effective in that kind of situation. So again, as the number of treatment combinations increases, that requires more and more experimental material, experimental units, and as the number of experimental units increases, in general, the homogeneity goes down, the heterogeneity increases, and therefore the precision decreases in those kind of situations. And so that low precision becomes more of a problem as the size of the experiment increases. Now, uses of the completely randomized design. Well, it's number one, it's as we indicated before, it's simple. It's a simple way of doing the experiment. You don't have to worry about too much in terms of, well, you don't have to worry about it at all, blocking and things like that. In addition, it is the most precise if the experimental material is homogeneous. So if you've got very homogeneous experimental units, and if there's really no reason for blocking and things like that, then you may very well want to use completely randomized design, because you're not going to have this lack of precision issue, and you will have maximum degrees of freedom for error, which again will give you more power. The CRD is useful if a large fraction of the experimental units may be lost due to or during the experiment, or perhaps don't respond. And so this can happen in the field, for example, in agricultural studies, where things can happen during the performance of an experiment over a growing season or whatever, where certain plots of ground have to be thrown out of the experiment. And perhaps somebody put the wrong kind of chemical on the plot, and so that it's got a different kind of treatment than what was planned. All sorts of things can cause experimental units to either be lost or not usable for an experiment. And then if the experiment is fairly small, so you've got so the experiment only requires a small number of experimental units, then the CRD may be very useful, because in that situation, with a smaller number of experimental units required, the probability of finding experimental units that are homogeneous increases, and so then you would again not have this lack of precision issue, and you would have maximum degrees of freedom for error. And so in smaller experiments, the CRDs may be more powerful, and if, as I said before, just easier to use. Now, let's take a look and remind ourselves of the structure of the ANOVA table for the completely randomized design. So this is the structure of the ANOVA table that you were exposed to in your first methods class, and this is the structure of the table that we looked at in our review. We're using slightly different notation now. We're getting away from the terminology of within samples and between samples and SSW and so forth. We're going to talk about the sources of variation in the model. So we have the treatments, we have the error, and then we have total variation. So these correspond to the components of the model. And so anyway, but we see here that the number of degrees of freedom for error is given by n minus t. So again, n is the total number of experimental units in the experiment. T is the number of treatments. And so the number of degrees of freedom for error for the completely randomized design is n minus t. Now, as we look at other types of designs, randomized block design, Latin square designs, and so forth, we're going to find that for a given treatment structure, this component, the number of degrees of freedom associated with treatments, is going to stay the same. In addition, for a given fixed number of experimental units to be used in an experiment, the total degrees of freedom is also going to stay fixed. And so what's going to change is that the number of degrees of freedom for error is going to diminish, because we're going to be partitioning variability in the treatment structure, and in the design structure, partitioning it out. And so the number of degrees of freedom for error will decrease. All right, so let's spend just a minute or two talking about how to actually do the randomization for a completely randomized design. And this is just the conceptual idea, how you actually implement this. It can be done on a computer. It can be done literally like I'm describing it here, right? You can do it in many, many different ways, whatever's most convenient. But it is important, and this is a very important thing for me to say and for you to hear, that you actually do have to perform the randomization. You can't just arbitrarily assign treatments to experimental units. There actually has to be a randomization procedure that is used to perform those random allocations. And so let's look at this conceptual idea. And so we've got a number of experimental units in the experiment. We'll denote that number by n. And so we want to number in some way those experimental units in the experiment from 1 through n. All right, so that's the simplest way to do it. We'll just number them 1 through n. And then what we'll do is we'll take n chips, so maybe poker chips, n of them. We'll label them 1 through n as well. Each one of those represents an experimental unit, and we place those chips in an urn, and then we mix the urn thoroughly. So an urn or a bag or a hat or whatever. All right, but you mix them up till they're because we want this to be random, right? And so then we just go through this process. So we select R1 chips. So these numbers R1, R2, and so forth up to R sub t would be determined before the experiment, before the randomization is done. All right, the experimenter would determine how many experimental units they want to assign treatment 1 to, and how many units they want to assign treatment 2 to, and so forth. And oftentimes you'll have equal replication, but again, it doesn't have to be equal replication. But once those numbers have been determined, then the process would be to select R1 chips from the n chips that are in the urn at random and without replacement, obviously. The corresponding experimental units are assigned to treatment 1. Then we select R2 chips from the remaining n minus R1 chips in the urn at random and again without replacement, and the corresponding experimental units are assigned to treatment 2, and so forth, until we get down to the last treatment that needs to be assigned, and there are R sub t chips remaining in the urn, and those are the experimental units that would get treatment T. So that is the conceptual idea behind this randomization process for the completely randomized design. And again, you can do this literally with chips in a bag or chips in an urn, but you could also do it with a computer. You could generate n numbers and generate random numbers for each of n data records, and then sort them in ascending order, for example. Take the first R1, assign those corresponding experimental units to treatment 1, and take the next R2, assign those to treatment 2, and so forth. Obviously, what you would have to do, you would construct an initial data set with integers 1 through n, all right, and then in addition to those experimental unit ID numbers, you would generate these other random numbers that I'm talking about that you would then sort. So that is one way to implement this randomization procedure via computer. And then what are the implications for this procedure that we just described? Well, as we said before, with this completely random method of assignment of treatments to experimental units, every possible allocation of each of the treatments to the corresponding number of experimental units has the same probability of occurring, and then the implication of that is that each experimental unit has the same probability of receiving each of the T treatments. So that is some basic information, defining characteristics for the completely randomized design. You've seen the calculations in a previous methods course, but now we're shifting our focus somewhat and considering the design features for an experiment. And so again, thinking about the treatment structure for an experiment, the design structure for the experiment, and the manner in which treatments are randomly assigned to experimental units, those three components really define the design of an experiment. And so it's those kinds of things that we'll need to be thinking about and considering when we are doing experiments, planning experiments, analyzing the data from experiments that have already been conducted, and so forth. And so the next topic that we might talk about will be the analysis of data from the completely randomized design. So that will be somewhat of a review, but we might couch it in slightly different notation, all right, to be consistent with the methods of analysis, the procedures that we'll be looking at for other designs as we go throughout the semester. So that's the end of this particular lecture video, and when we pick up in the next lecture video, we'll be talking more about how to analyze data from a completely randomized design.